All right, now let's do the second isomorphism theorem. And the second isomorphism theorem follows from the first one. But before we do it, I need to talk about the ways that we can make submodules out of other submodules. I don't think I've talked about that yet. So possibly when we did sets, I talked about the intersection and union of sets. And you might think perhaps just take the intersection and union of submodules and get bigger and smaller ones. But that doesn't quite work. The intersection works. So let's just check really quickly that the intersection of two submodules is a submodule. And remember that if I have two sets, S and T, the intersection, right, this is S and this is T, the intersection is the set of things that are in both sets. So that's what the intersection is. And the reason that that is a submodule and not just a subset is that if I have X and Y, some elements of the intersection, then it means that X and Y are in both, right? And it means X is in S and X is in T, and it means that Y is in S and Y is in T. So since both X and Y are in S, and S is a submodule, I can add those two elements in S, right? So X plus Y is in S, and both X and Y are in T, so I can add them in T. X plus Y is in T. And then since X plus Y is in both S and T, it's in the intersection. And it proceeds similarly, right? If you want to take scalar multiplication as well, right? You can do the scalar multiplication in S, you can do it in T, you get something that's in both S and T. And so, right, S intersect T is a submodule. And it's contained in, it's a submodule that's contained in both S and T. So S intersect T is contained in S, and S intersect T is contained in T. So it's smaller than, I can take two submodules and I can get a submodule that's contained in both. And then the union, you can check for yourself. Try to prove that the union of two submodules is a submodule. You won't be able to do it. It's not a submodule. But one way that we can get a submodule that's bigger than two submodules that I pick is take their like sum. So, and what I mean by the sum is take all of the elements of the form little s plus little t, where little s comes from S and little t comes from T. And that's a submodule as well. You can check that by yourself. It's not terribly hard to check it's a submodule. Just check that it's closed under addition and scalar multiplication. And then, oh, and I guess you should show it contains 0 as well. I forgot to check that for S intersect T. Right, 0's in here because it's in both S and T. So the 0's in there. And the 0's in this one as well. It's 0 plus 0. Anyway, S plus T is bigger, meaning it contains S and it contains T. So it contains both of the two original submodules. And you can see that it contains S because S is just the set of elements of the form little s plus 0, where S is anything in S. Okay, so those are submodules. And the second isomorphism theorem tells you how they relate to each other. And how they relate is that S plus T mod T is isomorphic to S mod S intersect T. And remember that S intersect T is a submodule of S. And so this quotient on the right makes sense. And S plus T contains T as a submodule because it's all of the elements of the form 0 plus something in T. And so the left quotient makes sense. So that's just checking that I'm not saying nonsense. Both these quotient modules are defined and they're isomorphic. And we're going to prove that they're isomorphic using the first isomorphism theorem. And the only hard part of this proof is coming up with a map. So I'll tell you the map. The map is, I'm going to define a map that I'll call F, and it's going to go from S to S plus T over T. And I'm going to define it by, let's see, I'm going to take, because you can't tell the difference between my little s and my big S, I'm going to write little x for an element in S. And F is going to map this element to the coset little x plus t. And that's an element of the right-hand side, of course. Okay, so in order for me to show this isomorphism, using the first isomorphism theorem, I'm going to need to show a couple of things. The first thing I need to show is that the kernel of this map is S intersect T. I guess I'm not going to do that first. The first thing I need to show is that this is an R module homomorphism. So I need to show F is an R module homomorphism, or R homomorphism for short. And the second thing I need to show is that it's surjective. And then I need to compute its kernel. And I need to show that the kernel of F is actually the intersection of the two submodules. Okay, so let's start with this map. Let's show that it's an R module homomorphism. So I need to compute F of x plus y. And by the definition of the map, this is x plus y plus t. It's that coset. But by the way that we add cosets, this is x plus t plus y plus t. It's just coset addition. And then x plus t is f of x, and y plus t is f of y. So we're done. That's addition. And then I need to do scalar multiplication. So f of let's pick a ring element r, little r, in the ring R, and f of little r times x is rx plus t. And then because of the way coset scalar multiplication is defined, this is little r times the coset x plus t. And that's little r times f of x. Okay, so check. F is an R homomorphism. Now let's check that F is onto. Okay, so to check that F is onto, I need to pick an arbitrary element in the codomain, and I need to show there's something in S that maps to it. Okay, so pick. Oh, so what does an element in this quotient module look like? Well, it's an element of this, and it's a coset of an element of this by t. So pick and I'm gonna call it little s plus little t plus big T. Right, that's what a coset looks like in this module S plus T mod T. But then there's something I noticed right away, which is that right, if I have a coset by something that's already in T, I can just absorb that into T. So S plus T. Okay, and I'm gonna call this something. I'm gonna call this Z. Z is gonna be that coset. Well, then Z equals S plus T as a coset, because if T is in T, then little t plus T is the same as the coset 0 plus T, right? T minus 0 is in T. So those are the same coset. So I can absorb the little t into the big T. But then little s plus t is exactly f of little s. Okay, but then I found an S that maps via F onto Z. So Z is in the image of F, which means that F is onto. So check, we're done. F is onto. And then finally, we need to compute the kernel. So let's remember the definition of the kernel. The kernel of F is the set of all these, let's say, little x in S, such that F of x is the zero, and it's the zero in the codomain. And the zero in the codomain is whatever the zero is in the module S plus T over T. And the zero, or the additive identity, in that module is 0 plus T. It's that coset. Okay, and let me just expand this some more. These are the x in S, such that f of x is x plus t. It's that coset. I need x plus t to equal 0 plus t. And those two cosets are the same if and only if x equals, if and only if x is in t, right? Meaning x minus 0 is in t. That's what it means for those cosets to be equal. So these are the x in S such that x is in t. But that's the same thing as S intersect T. It's the intersection. Okay, so we computed the kernel of F. And now let's just put it all together. By the first isomorphism theorem, let's go back to our map, right? S divided by the kernel of this map is isomorphic to the image of this map. So S divided by the kernel of F is isomorphic to the image of F. But we computed the image of F. The image of F was equal to the whole codomain because we showed that this map was surjective. And then we computed the kernel of F, and the kernel of F was the intersection of S and T. So we showed this isomorphism. That's what we showed. So we're done. And let me go on and off again for part 3.